Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. We are going to take a journey right into the mind of one of the most brilliant and honestly occasionally confusing figures in 19th century science. We're talking about the Irish mathematician William Rowan Hamilton. If you're a focused learner who loves unraveling how the universe actually works, you are in for a serious treat, because we're about to explore a dual legacy that quite literally shaped modern reality.
Okay, so get this. How exactly did one Victorian mathematician lay the groundwork for the Schrödinger equation, the literal foundation of quantum mechanics, and at the exact same time pioneer the math that makes 1996 pop culture touchstones like the video game Tomb Raider possible? I mean, no way, right? It sounds like science fiction, or maybe somebody mixed up some historical timelines. But the answer actually lies in understanding the extraordinary mind of this one man.
But before we dive in, we have to clear up a massive point of confusion right out of the gate. Hamilton's name is attached to two radically different concepts, and people mix them up all the time. On one hand, we have the physics Hamiltonian, which deals with total energy and the mechanics of physical systems. On the other hand, we have classical Hamiltonian quaternions, which is a four-dimensional mathematical number system used to calculate 3D spatial rotations. So two entirely different domains of human knowledge sharing the exact same namesake.
All right, here is our roadmap for today to keep these two legacies perfectly clear. 1. The physics Hamiltonian. 2. The bridge to quantum mechanics. 3. The quaternion epiphany. 4. Rotating the 3D world. And finally 5. One man, two universes.
Okay, let's jump right into part 1, the physics Hamiltonian, total energy and time evolution.
So what actually is the Hamiltonian in physics? Well, at its core, it's a function representing the total energy of a physical system. It stems from Hamilton's principle of stationary action, and it essentially acts as the generating function for time evolution. In plain terms, it basically gives us the differential equations of motion for a system. If you want to know how a physical system is going to evolve over time, the Hamiltonian gives you the unified phase space solutions. It's basically a mathematical map of every single possible state a system can be in.
So why should we care about this specific physical formalism? Because it has incredible practical superpowers. First off, it lays the total groundwork for statistical physics. You literally need Hamiltonians to understand thermal states in any general way. It also provides this beautiful geometrical picture of time evolution, which is exactly why it's heavily used in chaos theory, to see if a system's evolution is, well, chaotic. And I absolutely love this third point. It is completely crucial for planetary dynamics. Through what's known as secular theory, the Hamiltonian allows astrophysicists to separate the short-term, messy, chaotic interactions of planets from their incredibly long-term orbital evolution.
And this actually bridges Hamilton's physics with his geometric intuition perfectly. Back in 1832, while studying the wave surface of a biaxial crystal, Hamilton used his general theory of systems of rays to predict that the geometry of such a crystal would cause conical refraction. Now, that was something completely unobserved at the time. When it was experimentally verified the very next year, it was this massive triumph that proved light has a transverse wave nature. That ability to see the physical world through complex geometry, that was Hamilton's ultimate superpower.
All right, moving to section 2, the bridge to quantum mechanics, from the classical to the subatomic.
It is absolutely wild to trace the evolution of these mechanics over the centuries. We start all the way back with Newton's equations in the 1600s. Then, in the 1800s, we get the Hamilton-Jacobi equation, which is this really cool formulation where the motion of a particle can be represented as a wave. Fast forward to the 1920s, and boom, we have the Schrödinger equation. What physicists ended up finding was that, by taking a highly localized wave packet and evaluating it in the limit where Planck's constant approaches zero, that's called the WKB approximation limit, it simplifies straight back down to the classical Hamilton-Jacobi equation. Because of this, Hamilton's work is widely considered classical mechanics' absolute closest approach to quantum mechanics.
But here's the really mind-bending realization. In Newtonian mechanics, there's no visible underlying algebra, but Hamilton's mechanics inherently linked momentum and position. When quantum mechanics finally arrived on the scene, physicists realized it relied on that exact same algebraic structure. They were just swapping out classical numbers for quantum operators. He had essentially sketched out the architecture of the quantum world decades before anyone even knew it existed.
Which brings us to section 3, the quaternion epiphany, expanding the dimensions of math.
All right, picture this. It's October 16th, 1843, and we're looking at one of the most famous legends in mathematical history.
Hamilton had been desperately trying to extend complex numbers, which, remember, are plotted on a flat 2D plane, out into three-dimensional space. The solution had completely evaded him, until while he was walking along the Royal Canal in Dublin, he had a sudden, brilliant flash of genius. He realized he needed a fourth dimension to make the math work. He was so excited that he literally carved the fundamental formula for quaternion multiplication, I squared equals j squared equals k squared equals ijk equals -1, right into the stone of Brougham Bridge.
So let's break down exactly what he invented that day, almost like a recipe. Building a quaternion takes a few steps. First, you start with a scalar part, which Hamilton conceptually linked to pure time or just standard real numbers. Second, you add a vector part, but this isn't your everyday vector. It contains three separate imaginary numbers, I, j, and k, representing the three spatial axes. When you combine them all together, you get a four-dimensional hyper-complex number. And here is the real kicker. The order in which you multiply them actually matters. It was the very first significant number system that did not obey the standard commutative laws of ordinary arithmetic.
Section 4. Rotating the 3D World, the Modern Legacy of Quaternions.
So what exactly are these quaternion superpowers, and why do we still use them? Well, they are the absolute gold standard for calculating smooth 3D spatial rotations. Because unit quaternions form the simply connected cover of the space of 3D rotations, they totally avoid the computational glitches and pitfalls you get with older methods like Euler angles. Today, they're highly efficient and strictly relied upon for modern computer graphics, robotics, and signal processing. Literally, if you want to command the attitude control systems of a spacecraft currently orbiting the Earth, you are communicating in quaternions.
And yeah, that brings us completely full circle back to our hook. How does an abstract formula from 1843 relate to video games? Well, Tomb Raider, released back in 1996, is widely cited as the very first mass-market computer game to use quaternions to achieve smooth, glitch-free 3D rotation for its character rendering. Those fluid gymnastics you saw Lara Croft doing back in the 90s, they were directly powered by the mathematics Hamilton carved into a bridge in Ireland a century and a half earlier.
Let's just take a second to bring this all together, because keeping these two apart is the main thing I want you to take away today. One man, two distinct legacies. In the domain of physics, the physics Hamiltonian deals with energy, maps directly to quantum mechanics, and calculates planetary dynamics. Meanwhile, in the domain of mathematics, quaternions are hypercomplex 4D numbers used for rotating objects in computer graphics, spacecraft mechanics, and robotics. If you keep this distinction clear, you really understand Hamilton's true genius.
Which brings us to our final section, Section 5, One Man, Two Universes, the Enduring Power of Abstraction.
Which leaves us with a pretty massive question to chew on. Is the universe fundamentally mathematical? Think about it. Hamilton wasn't looking at subatomic particles, and he sure wasn't programming 3D spacecraft simulations. He was just following the pure, abstract logic of mathematics in the 1840s. Yet a century later, reality itself, from the quantum foundations of the universe to the digital architecture of our virtual worlds, turned out to perfectly match his equations. It really makes you wonder what abstract math being developed right now will define our reality a century from today. Thank you so much for joining me on this explainer. Stay curious, keep learning, and I'll catch you next time.